Hello, welcome to Chapter 3. It's segments and measurement. So if you look on page 83 in your textbook, I really want you to read this, but the overview of the introduction is talking about fractals. Okay, they're basically when you start with one figure and you either multiply or divide that figure into smaller and smaller sections that would be the exact same shape and be by scale factor shrink. Well, the text actually talks about the coast of Great Britain, and the reason why it's kind of a conundrum is that there are different ways to measure the coastline. So if you look at the most left picture, this would be the most estimated, right? It's the least exact. But when you're talking about a ship planning to sail around Great Britain and you're going to stop at certain ports, this would be the measurement. Okay, so the general length of the coast is called the coastline. But if you want to include bays and rivers and creeks and go all the way, land to land to land, that's called a shoreline. So there is a difference between a coastline and a shoreline, and no one really knows the exact measurement of the shoreline. Okay, we can make estimates of coastline. As you see, as the pictures go more and more to the right, we get more and more exact answers. But even on the last picture there, you see there's some land that is not included, and there's tiny little bays that aren't included on the indent. So it's just one of those mysteries that we're never really sure exactly. Okay, this section is called real numbers. Okay, when we talk about the real number system, I'm really hoping this is review from Algebra 1, that we can kind of wipe the cobwebs away from when we learned the number system for real numbers. We are also going to review some of the properties, addition and multiplication properties, and equality properties. We're going to learn a couple new things today in this lesson, so it is a little lengthy, but like I said, a lot of it is review to kind of give you that base before we jump in. So if you remember, there were two sides to the real number system. There was rational numbers and irrational. And then inside the rational were integers. Remember, a rational number means that you can represent a decimal as a fraction. So rational numbers were fractions. Irrational could not be represented as a fraction. And then integers are negative numbers and positive numbers that are like whole, include 0, and then whole numbers are just 0, and then counting numbers, and then natural numbers are just the counting numbers. Okay, the symbol for natural numbers is actually a double bar N, and I had trouble finding the symbol when I was first doing this PowerPoint, but if you can remember, it's a double bar N, it's the counting numbers, double bar W for whole numbers, and it's a double bar Z, okay, for whole numbers. I do have a slide that shows all of these double bars that I'm talking about. Okay, rational actually has a bar in there on that Q, okay, and it can be written as a fraction. And IR is not the symbol for irrational. This is what Bob Jones refers to, so I left it in the slideshow so that just in case it's really a Q, double bar Q prime, right? Just like in set notation, we talk about everything that's not Q. So everything that's not rational is considered irrational. And this is the system that we're used to looking at it in this manner last year. Irrational and rational don't overlap. They're totally different sets. They have nothing in common. There's no intersection. And then we also saw it this way. Here's the double bars. Okay, so I did a copy paste from one of the algebra lessons just so you could see some examples. So in the innermost circle, you see the double bar N and 2, 17, 100. Those are counting numbers. And then the double bar W includes 0. So everything that's in natural and 0. Okay, and then the next circle out, you see that double bar Z, that's your integers. So you've got introduction of negative numbers, and then on the outside of that is going to be your rational numbers. So you've got 1/7, negative 0.7, which would be negative 7/10, right? You can represent that as a fraction. And then on the right, you have your Q prime. So square root of 12, it's a decimal that cannot be represented as a fraction. So this is, again, just review of our real number system. Okay, so we're going to talk about the different real number properties. Okay, so the commutative property of addition is, if you think of commuting to work or commuting to school, if you and me are in the car, we come home, me and you are in the car, it's the same way no matter which direction you're talking. And then of multiplication, same exact thing. 5 times 3 is the same as 3 times 5. And then our associative property, we usually have another element with parentheses. So whether we add B and C first and then add A, or we add A and B first and then add C, it's the exact same answer. Multiplication is in turn the same direction. In fact, this chart, there's 3 separate charts that are on page 85, if you rather write them in chart form instead of my form. And then we have our very favorite distributive property. Okay, and when we talk about over addition, that means that parentheses are added, but then they're being multiplied to A. Okay, so if you look, I usually draw little arrows. Okay, and then we have identity properties of addition. When you add anything to 0, it's itself, and when you multiply anything times 1, you have itself. So those are our 2 identities. An inverse property. Okay, so if I have 5 and I add negative 5, I get 0. Okay, so 2 numbers that add together to give you 0 mean you have the inverse. And then multiplication is going to be when you multiply the fraction of that number. So 2 times 1/2 or 3 times 1/3. Okay, that's going to equal 1. A, of course, cannot equal 0 because we can't have zeros in the denominator. And then our equality properties. Now, these are going to be familiar, but I'm not sure how much we really focused on this in Algebra 1. We did talk about it, but it was very briefly, so we need to camp out here for a second. So if A equals B, okay, then A plus C or B plus C is going to be the same answer. So if A and B are the same value, they're both 5, and I add the same value C to both sides, I'm going to have the same answer. This property is really important when we were solving for X. Okay, and then multiplication is the same thing. If I multiply both sides by the same number, okay, what you do to one side, you do to the other. Remember that when we were solving equations? Okay, so this part right here is new. This is official geometry. When we talk about reflexive property, we're saying that a value is equal to itself, which seems pretty obvious, but we do have to prove that later on. And then symmetric is saying if A is equal to B, then B is equal to A. And this is similar to substitution, but not exactly the same. Okay, and last we have transitive. So we have this in-between value, and we say A is equal to B, and B is equal to C, then we can take out B and just straight up say A is equal to C. So in an example in real life, it would be like a relation is saying in the same family as. Okay, so Bill is in the same family as Bill is true, right? No matter whose name is used. I can put anybody's name in. Spencer is in the same family as Spencer, right? Okay, so and then symmetric would be like saying if Jan is in the same family as Joe, then Joe is in the same family as Jan, right? Okay, and transitive would be if Amanda is in the same family as Chris, and Chris is in the same family as Karen, then Amanda is in the same family as Karen. Okay, so it doesn't always hold true, if, say, Chris was adopted or by Karen's family out of Amanda's family. Okay, there's obviously circumstances that could change, but just to help you remember, I mean, I want you to think of using a family that lives in the same home, you know, mom and dad. Okay, so if you have any questions about this one, this is something you would want to put on your whisk. Okay, and an equivalence relation means that it's all three of those things. If I can say that a relationship is reflexive, symmetric, and transitive, then I have an equivalence relation. Again, we're going to give some examples so that we know what we're talking about. And then we have our favorite order of operations. Okay, the order is parentheses, exponents, multiply, divide, and then add and subtract. Now remember, dividing is like multiplying by a fraction, and subtraction is the opposite of addition, so they are the same order. We do all multiply, divide together, we do all add and subtract together, and I've also called it PEMDAS. Okay, so here is substitution. It's when you actually take the value of A equals B, then anywhere there's B, you can put in an A. Okay, so substitution means that they are equal, and you can rotate those two values, but it is a little bit different than the symmetric. Okay, trichotomy. This sounds super fancy, but it's really not. It's just saying that if I have two numbers, A and B, one of the following is true. That means I have three choices about A and B. Either A is equal to B, A is greater than B, or A is less than B. I mean, think about two numbers. Either they're equal, one's less, or one's greater. I mean, those are your only choices when you're talking about two values on a number line. But it sounds fancy, trichotomy. And then we have absolute value. Okay, and this is where our definition, you guys like to get confused here. Absolute value means it could be a negative number inside those bars or a positive number. Okay, if it's positive, it is going to be greater than or equal to 0. If it's negative, it's going to be less than 0. But remember, absolute value is like a distance. Okay, so when whatever number I have inside there, when I plug it out, it's going to be positive. So if I need to find the absolute value of 3 and the absolute value of negative 3, what is it? 3 is greater than or equal to 0, so the answer is 3, and the answer is 3 for both of them, right? Hopefully, again, this is review and we're not too confused. Now, to talk about the equivalent relation properties, reflexive, symmetric, and transitive, we're going to do those in class. So if you just could write those definitions down, we're going to do some more with that when we get into class and practice those. Okay, so I'm not going to practice them here on the slideshow. Okay, and for your whisk, just go ahead and read this. The word dense, I mean, if you think of dense in science, it's something that's like heavier or thicker, it usually weighs more. Okay, in math, it describes a set of numbers so that any two numbers of a set, there can always be found another member of the same set between them. Okay, so if you talk about rational numbers, and I have a number 4 and 5, how many rational numbers are there between 4 and 5? How many fractions, right? Rational means fractions, can go in between 4 and 5? Well, it's infinite. It's infinite amount. But in integers, they're not as dense. And so I want you to talk to me about why. I want you to explain what you think about that word dense, and I will email you a response. Okay, so I will see you in class.